Hello, everyone. This is Bryant and Chris, and this is our stats final project on education inequality. So first, a short introduction for what education inequality is. It is the unequal distribution of educational resources and opportunities. So this inequality can be a serious barrier for social and economic mobility. And what studying education inequality does is it allows us to better understand where the issues are and how to address them.
So the first method we used was a t-test for population slope. The statistical question we used was, is there a positive relationship between median household income and math proficiency in US school districts? We randomly sampled 50 school districts among all of about 13,000 US school districts. For each school district, we found the median household income within the district, as well as the proportion of students who meet minimum standards for math proficiency. This is the raw data that we used. On the left is a graph of all of the different school districts that we randomly sampled, as well as the income and math proficiency. And on the right is the linear regression model that we ran, and the equation that we found is on the screen there, as you can see. So this is the actual hypothesis test. First, for parameter and hypotheses, let beta be the true increase in proportion of students proficient in math for every increase in thousands of dollars in median household income. Our null hypothesis was beta is equal to 0, and our alternate hypothesis is that beta is greater than 0. We chose a significance level of alpha is equal to 0.1, which is a larger alpha, since a type 2 error is more severe because failing to find educational inequality when it does exist is worse than falsely believing an instance of educational inequality exists when it doesn't exist. Next, for assumptions, based off this plot of residuals that you see below, we found that distribution of E at any particular X has a mean value of 0. Standard deviation of E is the same for any particular X. Distribution of E at any X is normal, and random deviations of E1, E2, E3, etc. are independent. So for our test statistic and p-value, we use the formula that you see on the screen to get these values. And calculating the p-value, we found that the p-value was 0.0549. Because the p-value that we found, 0.0549, is less than our alpha of 0.10, we reject the null hypothesis. There is convincing statistical evidence that there is a positive linear relationship between median household income and math proficiency in US school districts.
Next, moving on to our second test, which is a chi-squared test for homogeneity. So our statistical question for this test is, do rich states and poor states have the same distribution of educational attainment? So here's our data. We compared between Massachusetts and Oklahoma, and a number of each level of degree is included on the slide. So let's see how we define our population first. So we're comparing the rich and the poor state. So one population is the rich states and one population is the poor states. So how did we define a rich state and a poor state? Well, we had the top 12 states based on median income be a rich state, and the bottom 12 states based on median household income be poor states. So our sample is one rich state and one poor state, which are Massachusetts and Oklahoma respectively. So let's look at our population parameters and hypotheses. So for the population parameter, we let PR1, PR2, PR3, and PR4 be the true proportion of individuals living in rich states who have no degree, a high school diploma, a bachelor's degree, and advanced degree, respectively. We similarly define PP1, PP2, PP3, and PP4 based on the poor state. So for H, we have that our null hypothesis is the population proportions in no degree, high school diploma, bachelor's degree, and advanced degree are the same for both Massachusetts and Oklahoma. And our alternative hypothesis is that at least one proportion differs. And as Chris mentioned before, our alpha is 0.1 because of the issues with making the type 2 error. So here are three assumptions. All expected counts are at least 5, that it's a simple random sample, and the sample size is less than 10% of the population. So first, we'll look at the 10% condition for independence. the total population of the top 12 states is 58,612,750, whereas Massachusetts population is 4,934,755. As we can see, it's less than 10% of the population. Similarly, the total population of the poor states is 31,940,594, and the population of Oklahoma is 2,639,889, which is also less than 10% of the total. So once again, we look at our data, but now we included the expected counts. So as we can see, all the expected counts are significantly greater than or equal to 5, meaning all of our conditions are met. So our actual test is that the chi-squared equals to the sum of the observed minus expected squared divided by expected. And using this formula gives us the following values. So our chi-squared statistic is 274,072.1822, which gives us a p-value of around 0. And our degrees of freedom is 3, which we calculated by subtracting 1 from the row and 1 from the column. So we get 1 times 3 is 3. So because the p-value is about 0 and it's less than alpha equals to 0.1, we reject the null hypothesis. There is convincing evidence that at least one proportion of highest educational attainment differs between Massachusetts and Oklahoma. So for our third test, we did another slope-related statistical method, but this time we did a confidence interval. So our statistical question for the third test is that what is the amount of change in SAT score over time for non-native English speakers? So here's our data based on the publicized reports, which go back to 2017, and we also excluded COVID here. So for our population parameter and assumptions, we let beta be the true mean change in SAT score for all non-native speakers for a 1-year increase. So once again, we have the assumptions, which are that the distribution of E at any particular X has mean value 0. The standard deviation of E is the same for any particular X. The distribution of E at any X is normal, and the random deviations of the errors are independent. So when we look at the data, we use the formula B plus or minus T crit times the standard error of the slope. And based on that, we get a confidence interval of negative 46.6535 to 7.0212. So what is our conclusion based on this? We are 95% confident that the true mean change in SAT score for non-native speakers is between a 46.6535 point decrease and a 7.0212 point increase for a 1-year increase. Because this confidence interval includes 0, we cannot be certain that there is a statistically significant change in SAT scores at the 0.05 level.
Moving on to the reflection. Based on the first test conducted, a t-test for slope, we found that there is convincing evidence that living in a richer area has a positive linear relationship with math proficiency. This shows that class may play a factor in education inequality since economic class correlates with math proficiency. Our second test found that based on Massachusetts and Oklahoma, there is a difference in proportion between highest level of educational attainment in poor states and rich states. It is possible that states are richer because of this higher proportion of highly educated citizens, that these citizens are highly educated because living in a rich state affords more resources for education, or that people who attain higher degrees tend to move to richer states. Our third statistical procedure found that we don't have convincing evidence of a change in SAT score over time for non-native English speakers. These tests indicate that there is an association between quality of education and geographic and economic barriers. Education inequality persists as an issue facing students, but we are unsure as to how this is changing over time. For further study, a potential flaw of our first test is that we use the median income of families in the area of the school district, but we did not account for families that send their students to schools outside of their school district. This could potentially impact our data if wealthier students are more likely to send their children to private schools outside of their district. Future research into the association between income and math proficiency should more closely link individual households' incomes and their students' outcomes. A potential flaw with our third test is that SAT tests often vary in difficulty, so natural changes in total average score were not considered in our analysis. Further study could use more reliable metrics to draw conclusions. Further study should also look at the intersection of racial, geographic, and economic barriers. Our tests all only focused on one aspect that potentially leads to inequality, but by combining different categories and types of inequality, a clearer picture for the root cause of education inequality can be drawn. Furthermore, our studies also largely focused on America, so for further study of education inequality on the global level is necessary to inform a broader understanding of the issue. Here are the works that we cited, the different sources that we use to collect our data for all of our different tests. Thank you very much.